Hello, my name is Tuomas Sivula. I am the Cactus person number 3. Uh, I have also been Aalto University person, and there was Aki Vehtari over here, and I am a person also from this research group called Bayesian Machine Learning Group. And uh, after that, I have been doing some stuff as a consultant and doing lots of different kind of projects. And now I am doing projects solely on this energy domain with batteries, and I love it. I highly recommend also other people that are interested to join us, and we will show the same QR code in the end of the slide. So please click that if you are interested. And I got a hint that you would be interested maybe seeing some practical applications that would be specific to our domain. And I hope that this presentation will give some sort of intuition of an example case that could be applied in this setting. And uh, so, what is the gist of this stochastic optimization in this battery energy storage system domain? And what we want to achieve is to make the operation so that it gives us more profit, it gives us stability, and we want to avoid problematic situation when we want to keep the devices healthy and safe and sound all the time. We don't want to drive them to such a level that these are not going to be sustainable for a long period or something like that. We want to also take into account that these are uh, sensitive devices that needs to be taken care of. So these operations, they uh, have lots of different uncertain factors including them. Jussi mentioned that there is a big deal of having this whole chain of usage of the energy and keep that steady and stable all the time. Uh, some of the key components that play a role in the uncertainty is the consumption and production and in the market prices, for example. And for this, we often want to use stochastic models and take a grasp of that uncertainty that relates to those unknown phenomena. And I know that most of us are very proficient and like experts in the data part of this topic, but I wasn't sure about if all of us are like the experts in the uncertainty and the stochastic parts. And because of that, I will quickly go do a small walkthrough about what is the main points in doing stochastic optimization and having the uncertainty part with that. So you may have heard about this famous quote that all models are wrong, but some are useful. And this is a nice sentence in the fact that it tells us why and what we are doing. The aim is not here to have like a perfect forecast that we exactly know that, okay, this consumption is going to be level X in 3 days, because that's not sensible. We want to instead quantify and manage and control the uncertainty that's related to that. We do that by describing the relationships in the data, how this data has come to alive, and we want to make the model acknowledge the randomness and the imperfection in that. Then, of course, some models are more useful than the others, and because of that, we want to do some assessment of the models and select best model. And oftentimes there are also uh, considerations that take a role when doing a model selection, not only in the performance but also in practice. When you do a model, you want to make it first quick and rough and dirty, and then check if this is enough, and then maybe improve on. So it's not all about the performance of the model, but also how it applies in the actual business domain, for example. And then a bit about the technical stuff. So we have these nice ideas about doing models and applying very fancy mathematical formulas. But then, what good is those if we don't have ways to use those and utilize those? So here comes the nice part. So we have this probabilistic programming framework, and this is a way to make these easy to be implemented. We want to focus on what to model, not how to compute it, and that's like very high level goal, but it is quite achievable with some tools that we have. And this presentation now highlights a use case in which we have applied such one framework that gives us nice results without us to focus too much on the compute part, but instead on the modeling part. We describe what we want to do, and the programming environment then does the heavy lifting and does the computation. Then there's some name dropping. You may have used or heard about these. I'm not going to go into details, but there are selection of with your own type of modeling frameworks, which can be applied to more or variety of settings. You can build like a your own dream model out of these. You can do a small adjustments and tweak them as you like. Gives you a lot of variety on how you implement stuff. And then there are these ready-made models, more ready-made models, which gives you a template of what you could do. And these are very fine-tuned and also are very target specific, that you know already what you want to achieve, and then you pick the tool which will then fit to your purpose. These ready-made models here are quite a bit concentrated on time series data, but there are of course different kind of domains in which there are lots of different tools. And for this presentation, I wanted to pick a nice and very describable example, and for that I picked and used a real case from our operations in which we apply the stand model. And the next will then continue on an example in which we have a case with certain markets of ancillary service that is related to the battery energy storage system operations. So in the first presentation, Jussi talked about these ancillary services that can be then precipitated into. We have a battery, and then there is the grid that needs to be stabilized. And in order to stabilize those small imperfections that happen in the grid, there are different kind of ways to counter these different instabilizations. And one way is to the operation controlling party to uh, sell this kind of allocations, or offer these kind of allocations in which we can take parts into, and we say that we will promise you that we will be available for consumption or production on your demand. And then by doing this kind of allocation, we get compensated monetarily. And then if they then activate and tell us that, okay, now you need to push some energy, or now you need to take some energy, we get also compensation for that energy. But here is the gist. We don't know in advance how much they will actually tell us to produce or consume the energy. And this affects quite heavily on what will happen then after this period of allocation has been done. If we want to go on and operate these devices for long term, we want to plan ahead what will happen at each point of time. We can't go into a situation in which we have promised already that we will be available to like consume energy at some point, but then for some reason the devices are not able to deliver what we have promised. If this would happen, we will be facing like penalties, which are very heavy, and these are not something that the grid will also suffer from these unexpected failures to commit to what you have promised. So what we need to do is we need to model this uncertainty relating to this kind of uh, allocation and this kind of unknowing of how much will be activated. And for that, we use models. We use historical data that shows us how the different kind of environmental data points have affected to this activation in history. When we have done a model to see what kind of activation would be forecasted to different periods, we can then decide when we want to precipitate and how much we will be able to deliver at those points. So this is an example of historical data related to this specific case. We have this activation that can be done either up or down. We can be told to consume or produce energy. And we can see that the ratio of activation to, so ratio of 1 here means that all that we have promised will be activated. And ratio of 0 says that you weren't activated at all. And from this figure, we can see that there are quite a lot of situations in which we don't get activated at all, and quite a lot of also those that gets fully activated. And we can see that this is very uncertain. And depending on how much you have allocated, this might change the situation in the future quite heavily. We might be in a situation when we have been over the period of allocation that we are already running out of the all the energy in the batteries. And then we can't continue on what we have promised in the future, for example. This clearly shows us that we need some kind of model to overcome this problem. And what we do, in this use case, we do a simplified model to show what we could do and what we apply in our operations. We build a model. We use now this build your own toolbox setting with Stan. And we build a model in which we try to check out how the activation behaves with different groups. We group the data by weekday and hour. This is simplified setting. And then we build a mixture model in which we have 0 activation and 1 activation and then something in between. The activation for the part something between will be beta distributed, and then we will use Stan to describe the model in detail. Stan is quite nice in a way that you can utilize your own fine-tuning for small details in the data. You can put in there prior beliefs that you know that will affect how the system of the data really behaves. You need to code the model, and then you tell the program to do calculations by giving it a data, and then the model will run and give you results about the unknown parameters. Now, this is a showcase that shows how the example data that we provided for this model seems from the perspective of the fitted data parameters. In this case, we had 2 groups. We had day of the week and the hour. And then we see that for different days and different hours, the activation ratio, or having no activation at all, having full activation, or then having something between activated. The hourly and weekday effect is clearly showing in the results. We see that the activation is clearly dependent on when you get activated. This motivates us that we really need some kind of model to take into account when doing the operations. Then when we apply this model to get the results in the operational setting, we need to build up way of utilizing this information about the activation. For that, well, we have a simulation in which we simulate the battery in an environment with all the unknown parameters. One of those would be the unknown AFR activation. Then we simulate the battery uh, over time and check out which kind of configurations and allocation would result in best profits or best utility. The next slide showcases a situation for a simulation of the potential utility of one single unit over time of 3 days. And on the y-axis, we have the state of charge for that unit. And on the heat map, the higher color corresponds into a situation which is potentially more usable in the monetary or utility new way. And we can see from the figure certain areas are clearly more provident and provide us with best utility. You can see a trend that this kind of setting, for example, here is definitely a state in which you don't want to be at 0% of a state of charge. Then we optimize the usage of the battery by selecting paths that will then provide us the best utility and still is achievable and provides us with different kind of allocation that are able to be delivered. The simulation will output an optimal path by selecting the setting in which we select different kind of operations for the battery and then select which is the best SOC level at each time point. On the top here we have the energy prices and the prices that will be delivered by the allocations, and then we are connected to a facility that also consumes energy. In here we can see the path of the SOC that we have selected to be the optimal one, and then on the lower hand side we see how we control the usage of the battery at each time point. This will then be in the end compared to the real setting in which we run the battery at a real setting, and then compare the results by checking out if we would have used a very naive estimate for the AFR activation. And this example showcase illustrates that if we would have simple selected that we have a activation at some mean level, for example, a single value, let's say that the historical data tells us that the activation will be mainly around 20% or 50%. If we would have used that, we would have been able to deliver all that we have done, but the utility would have been a much, much lower. And this figure here shows us the improvement ratio by selecting the model that we now showcased in the example. We see that there is clearly need for taking into account the uncertainty related to this one particular factor. This is a simplified example of only one factor that plays a role, great role, in the operation of the batteries. And there is a room for improvements in lots of these different settings. But this presentation that I give is not going to be a full detailed explanation of what are all those components that we need to check and monitor into. If you are keen on playing around with different models for taking into account these uncertainties, you will love this kind of environment in which there are lots of moving puzzles and involve lots of details about combining different sources of uncertainty into one operational system. And if you are if you are in a setting that you would love to hear more of us and maybe discuss a bit further about joining us, please click the link and we will get in touch. Thank you. Do we have time for questions?
For a few quick questions, sure.
Yes.
Very good with this. Did you have a chance to try neural links? Sorry? Did you have a chance to experiment with neural kind of probabilistic models like LCM or RNN?
Yeah, we have tried for a different setting, not for this AFR activation, but with different setting, and it was also time series um, prediction. That was one part of the same simulator optimizer network, but it did work. But then again, we also had ways to do the same thing with different models, so we ended up with a different model. But we have tried out it.
Please. Actually, great presentation. It's been a couple of years since I used PAN. So when you get the optimal operation strategy, is it optimal in the sense of it provides the best expected profit, or can you tell the model to, okay, this is a case where I do not want bad things to happen. So
Yeah, so
the strategy that will avoid the worst case.
Yeah, we have lots of different switches that we can select upon. The building of the utility and measuring the utility is very case dependent, and we can have lots of different decisions that we want to put into that. It will not be only solely based on the monetary value. We can, of course, do it so that we simple and do the simple solution and take the best solution that gives us the most money. But we also want to include there some penalties and stuff like that. But in the end, we need to get some sort of solution. So oftentimes we use penalties to include some kind of effect from these unwanted events of happening.
Great, thanks.
Yeah. Thank you.
Okay, thanks.